hope you tried this. This stuff gets complicated in a hurry because we're going to move right out of here and get into transients in the next day or two. You have to keep up with this if you don't. I mean, so many people try cramming it, it hurts. It really does. You see them not focusing on this stuff and they need to. All right, so any questions at all? Any questions? How many did the homework? At least give me an idea of what I'm talking about. One person? If you didn't do it, I'm not going to criticize you, but I encourage you to do it. Does anybody have any question at all? Are you kidding me? Usually I get a cajillion questions about impedance matching. No? All right. Well, I can't assume you know it. You don't have to take one either. Nothing. Did you do it?
Too busy with other.
Too busy. All right, we're going to do one at least, possibly two. If you have a Smith chart and stuff, get it out. We're going to need to know how to do this. And these things can get very, very confusing if you don't keep up. I just want you that ahead of time. All right, so for impedance matching, first one I want to do is 2.37. This is something I didn't cover in class, but it's fairly straightforward. It's quarter wave matching. All right, this is 2.37. I did this in my office, and several people were there. I don't remember how many, but so this is a problem. This is a standard problem. So here's what happens. You have an impedance from a transmission line, and I'll just call it Z0 here. Well, let me use a different term for this. I'm going to call it Z sub C. This is the characteristic impedance of a line from a source. And you can assume it's very, very long. And here's the source voltage plus or minus Vs. Doesn't matter. Now we have a load over here. And this load must be strictly real. You cannot have an imaginary part to do this quarter wave matching. This is very important. So over here we have some load. I'll just call it R load here. And now we want to put between these two something that is going to be exactly land over for long. It's going to be a transmission line with an impedance that we have to calculate. So this is the characteristic impedance of a section of line that's going to be only a quarter wavelength. But I want to say this much. You don't do this with coaxial lines. When we actually fabricate microelectronic components on boards, normally you have a large planar piece of copper, and you have a dielectric above that, or substrate it's called. And then you have copper on the top. You etch away all the copper you don't want, and what you'll do is have varying thickness lines. There will be your conducting transmission line's upper point, and the actual copper beneath it will be the lower point. But by adjusting the width of that line, you can create any characteristic impedance you want. So this is common for anything that's going to be on something called Duroid board or FR4. Well, maybe not FR4. Do you know what FR4 is? The green board? How many do? Anybody? Okay, a couple of you do. That's typical. It's a lossy substance. You don't want to do this if you've got stuff at high frequencies and you don't want to lose much power. But it is used too. There's a Duroid board. Does anybody know what RF Duroid board is here? That's expensive. It's about $100 a square foot. And that has very low loss dielectrics, but it's used to create all sorts of high frequency circuits. And it's used sort of to mount and then make the transmission lines connect points. You all with me? All right. On that later. So back to this guy right here. Now, when you think about any kind of transmission line, what we'd like to do is have this input impedance right. You didn't move. You're smart. It's going to be raining markers in a second. Anyway, what we want to do is make this impedance right here looking in, and I'll call it Z in. I want that to be equal to ZC so there's no reflections. You understand the reason for it? Everybody? Remember, if I look that way and I see ZC, this characteristic impedance here, then I got no reflections. You all follow? That's the goal of impedance matching. No reflections. So when I take a look at this, I said that Zn here, the input impedance of that, well, it's always going to be Z0. Now that's this characteristic impedance, Z0. Then it's times ZL. I'll put this form down and I'll replace this by RL. Plus Z0 times the tangent of beta L over Z naught plus J, I forgot the J there, plus J ZL times the tangent of beta L. And that's the input impedance. Does everybody agree with that? Class? Now, I'm going to adjust a few things. First, I said that that's RL. And the reason I did it, I want to make sure you understand you cannot do this with an imaginary component for a load impedance. So I'm just going to call that RL. Now, after that, I note the distance. All right, that transmission line that I'm going to calculate the characteristic impedance of is only a quarter wavelength long. Y'all hear me? This should ring bells with the last quiz. When I take a look at this, beta L, therefore we come, beta is 2 pi over lambda, and L is lambda over 4. So that's pi over 2 radians. You all with me? Everybody? Now, one thing that you should have, this should stick with you after that last quiz. This tangent of beta L is going to infinity, isn't it? How many know that? Tangent of pi over 2 or 90 degrees is going to infinity. That one's going to infinity too, right? Now, I'm not, we could do Local algebra, but you really don't have to. If you look at that, it means this term and this term are insignificant. Do you all agree with that? I'm going to see this. Now, if you just look at this, the tangents will cancel out. They're both going to infinity at the same rate. So it means that input impedance is simply going to be equal to Z naught squared over RL. You all with me? How many see this right? This is not hard to see. Just be attentive. Don't be distracted. Look at your phone, talk to anybody and his brother about the game or whatever. Just watch this and pay attention. Now, this is the Z naught we're calculating. Here's where we came from, right? And that's Zn. Well, we want Zn to be this. Do you all see that? We want Zn to be equal to Zc. Then it's matched. Do you all see this, class? How many see this right? Okay, so now I come over here and I simply take that equation and I say Zn is therefore Z sub C. It's the impedance I'm coming from, and that's equal to Z naught squared over RL. So to calculate the value of Z naught, the impedance here, we simply take the square root of RL times Z, in this case, ZC, which would be the characteristic impedance of the line I'm coming from. And that's it, in a nutshell. For that specific problem, what did they give you for the load impedance for this problem? Just look at it. Yeah, please.
70 ohms.
70?
170.
170? Okay, now get your calculators, just take a look at this. And what is the characteristic impedance you're coming from over here? Say it. What is the impedance over here you're coming from? What does he say it wants to be matched to? Anybody? 50?
Yes.
Okay, so this is 50. Now get your calculators and just see if this should work. That means the characteristic impedance of this quarter wave section should be equal to the square root of the load, which is, I'm just going to put 50, right, times 170. Let's see if we get it right. Y'all follow me what I'm doing? But it only works when the load is stripped real, like an antenna with 300 ohms or something like that. Impedance. If it had 300 plus J50, this won't work. You'll get it close, but it won't work well. Anybody? What do you do? Just do the math. Multiply 170 by 50 and take the square root. Anybody? Can somebody please do this one? I'm encouraging you to use your calculator. 92.19. Anybody confirm that? All right. Anybody have the solutions? I know I posted them. Anybody just bet? I bet you it's wrong. I'll bet $5. Is it right? Anybody have access to the solutions? They're on OneNote. I promise you. Did you guys get that or not? Did you guys get it? All right. I mean, do you have the solutions or not right now? Okay. All right, you with me on this one? Now, quarter wave stuff is a very, very important downfield. I mean, when you're doing a lot of stuff in the real world, this is a trick that solves many problems. When you're dealing with 300 ohm antennas and you got a 50 ohm line, you got like, normally speaking, 50, then you have 75 ohm feed lines sometimes, but this is about the easiest way if you have a strict real load to do matching on boards. I want to do another problem, because the way you're going to learn this is seeing problems work and making sure that you understand the concepts. Now, we can do impedance matching by either putting components in the circuit, but that is costly for most applications, or we can use transmission lines that are shorted or open to replace the component. And now we're just going to kind of go through the whole thing and do it. Remember, when you're doing impedance matching, if you have a load here, and a characteristic impedance here, the first thing you always do is normalize it. But the length that you always move, L, from here, is such that looking in here, and I'll call it Z normalized. Z in normalized is going to be 1 plus or minus JX if you're doing impedance matching. Impedance means you're putting a series element. You're going to add an element in series is adding impedance. Y'all hear me? The only thing you're going to do is get rid of that plus or minus J component by adding a component that will exactly nullify. If it's plus J5, you'll put a component that has a normalized impedance of minus J5 in series so they cancel. Y'all with me on this? Now, if it was admittance, then instead of having Z in, I would have Y in here. And Y in would be 1 plus or minus JX. And you would simply add a component in parallel or shunt that would eliminate the J. If it was plus, say 1 plus J7, all right? You would add a component that's minus J7. Y'all follow me? Can you see my writing back there? It's Y in, it's 1 over Z in. Here, I'll draw it a little bigger. So here, Y in is 1 over Z in. That's what it is. And I'm saying it has a value of 1. In Wentworth's book, you have plus or minus JB. It's fine. You can use that symbol. Whatever this is, if it was 1 plus JB, you had a parallel admittance that has minus JB. That's the idea. Everybody with me? And we can do that. We can add this, either elements, capacitors or inductors, or we can take transmission lines and get the same exact values. Do you all hear me? We short or open the end of the transmission line to do this. Now I'm going to show you by doing problems how this is done. Everybody with me? All right. Okay. Now, let's try. Let's do 2.38. So I'm going to erase this. I can leave this up here, but we're going to do 2.38 as a class. All right, so I need my trusty old Smith chart right here. Okay, get it out. I always try to draw this one circle, it gives you perspective. This is J1, down here it's minus J1. This is the infinite point, and this is the 0 point on a Smith chart. Make it more, I guess, cluttered for that. So for this problem, give me the specs on this one. We got a line, and what does it say it has? Xenon is what? Anyone?
100 ohms.
70?
70.
No, that ain't right. This is problem 2.38.
Yeah,
What is the
100.
characteristic impedance? What?
Never mind. I don't know.
I can't.
100.
100 for xenon?
Yeah.
100 ohms, okay. And what is the loaded P, ZL?
200 plus J 160.
Okay. Now, first thing you always do is normalize, right? So my first step, and oh, by the way, they want this in parallel or series? Just tell, is it shunt or?
Shunt.
Shunt is parallel. Y'all hear me? So we're going to be working in the admittance domain. And we're going to add actually a transmission line to do this, but I want you to hear me now. Everybody with me? So first we find normalized ZL, right? And that is going to be what? 2 plus J 1.6. Do you agree with that? Where is that on the Smith chart? Get it out and look. All right, on the Smith chart, 2 is about here. This is just approximating. If you look at this, this is R equal to 2. And J 1.6 is about here. And remember, this is the trajectory that comes in perpendicular. So this is 0.1, this is ZL. See if you can find that first of all. Make sure you can see that. All right. Does anybody need a Smith chart, by the way? That's right, I didn't bring it out. Anybody at all? All right, get your compass out, and first make sure you can locate that point on it. Can everybody find that point? Give me a show of hands if you can find it. Anybody not able to find that point? All right, now, the next thing is take your compass and go from the center right here and draw. What you're going to do is to put a circle right here of that radius. So this is your magnitude of constant reflection coefficient right there. Can you all do that? Can you all follow me on this? You're going from the center to this point and you draw a circle of that radius. Does anybody not understand this? Anybody else? Don't be afraid to ask. I'll send somebody your way to help. You have to learn this. All right? Go ahead and do it. I encourage you to get a good compass because I will take off points if it's too far afield. The thing spirals and gets bigger. Okay? Now, also do this. Take a straight edge and draw a line right like this through that. Can you, everybody with me? I just need a straight edge line from the center to that point where ZL is and take it, make it right through both sides of that circle, your Smith chart. Anybody having trouble with that circle? All right, you need to draw. Do you have a straight edge circle? You got it. Anybody else need a straight edge or something? I honestly, the straight edges, I like the flat plastic ones that I have up there. But you can use anything that works. A ruler and the edges of some books will work. Y'all, everybody with me on this? Now, no, this is ZL. This point right here is YL. If you want that value, just take this value. Can somebody do this on the calculator? If you take 1 over ZL, you get YL. So YL would be 1 over ZL. What is that? I mean, I'm sorry, 1 over the normalized value. So that would be YL here would be 1 over 2 plus J 1.6. Can somebody tell me what that is? That could be minus J something. And a value that's probably around 0.5 for real. Anybody?
It's 0.3. Do you want it in rectangular or polar?
Rectangular.
Okay, 0.3 minus 0.24. Sorry, J 0.24.
All right, now that should be this point. And here's what happens. There's going to be a circle. I really don't want to make it too busy. It's going to have a radius like this, much larger. And the real part will be 0.3. And then if you look down here, you got this trajectory that would basically do this, come through here. Down here, you would get minus J 0.24 approximately. Can you all see that? You all see it? Does anybody not see it? You see it back there, guys? Over here, far side of the room. You guys got it? Okay. Now, here's the point we're going to start at when we start moving, because we're going to put something in parallel or shunt. So now I need this mile marker. So if you go right through here, give me the mile marker wavelengths towards generator. It's going to be 0.4 something, I'm guessing. 0.43 maybe.
0.457.
0.457. Anybody confirm that?
Yeah.
So we got 0.457 lambda. That's the mile marker we're starting at. Y'all hear me? With me, class? Now, we're going to move along this circle towards the generator until we hit the point where that circle, a constant radius, intersects the one circle. And this is going to have a value of 1 plus j something. And if you shoot a line right from here through here, you're also going to have to give me this point in wavelengths towards generator that I ended up at. So first, locate the point where that big circle you drew right here intersects the one circle. This is the one circle. It's the one that goes right through the center.
It's
All right. Now, pick it. And by the way, make sure you look carefully. What is this point right here? It's going to be 0.1 something, but I don't know. Anybody?
0.171 maybe.
Anybody confirm that?
Yeah.
Point about
0.171.
0.171 lambda. That's where you're going to land. You started here at 0.457. You landed there. Y'all with me? Now we're going to calculate the length. Can you see this in this circle? If you have a question, just ask, please.
No.
You don't have to worry. If you don't see something, just ask. There's nothing, I'm not trying to do anything other than help people. And if you don't ask, I can't answer questions. I need to know what you don't know. Or try to at least really deduce what you don't know.
That's,
All right,
excuse me real quick. That second point is through the one circle that goes into the middle.
Here's how I got it. I went from the middle, and I shot a line straight through the point 1 plus j, whatever it is. And we're going to get to right out here. By the way, what is this point? 1 plus j on the one circle that it intersects?
plus J.
3.3.
1 point plus j what?
1.3.
Yeah, here's
1.3.
1.3, j 1.3?
Well, it's close to J 1.4, so I don't know why we would.
3 approximately? Is that about it?
More.
1.38, but yeah.
Yeah.
1.38, all right, 1.38. I'll go with 1.38 for now. All right, that's that point. Now, make sure you understand. Here's how we get the length of the line that we're actually going to move. We've got to move this far. And this length L is the mile marker you got up at, which is 0.171 minus the mile marker you came from, which is 0.457. Right? But what's the problem with that? It's negative, right? So what do? Class?
Add 0.5.
Add half. Yeah, add 0.5. So we add 0.5 to it. Now, what do you get for that in terms of wavelengths? Anyone? Can you just do the math on this?
Dr. Baginski, that, the 1.71, I can't really read.
0.17.
Sorry, 0.171.
Here.
Yeah, can you? Thank
This
you.
is 0.171 lambda, and it's in the wavelength towards generator outer circle. The lambda isn't on your Smith chart, it's implied.
Yeah, well, yeah.
Okay. Did you have a question, sir? Yes.
It's 0.214. 0.214.
0.14 lambda.
Yes.
So that's how far we moved, 0.214 lambda. Are you with me? Now, here, the value of the admittance that we have to get rid of is plus j 1.38. Y'all hear me? If we added, it's an admittance now, if it's an admittance, it's 1 over impedance. If we added a capacitor, well, actually, a capacitor would never do it in parallel because it's going to have a positive J sense for admittance. But if we added an inductor that had a value of normalized admittance of minus J 1.38, we could get rid of it. You all hear me? I don't like inductors in parallel. Now, the problem may state that it wants a minimum stub length or a minimum distance from the load. What is the problem? Can somebody read the entirety of the problem?
A load impedance VL equals 200.360 ohms is to be matched to a 100 ohm line using a shorted shunt stub tuner. Find the solution that minimizes the length of the shorted stub.
Okay. Hear that? He wants the length of the stub, the transmission line with a short on it that we're going to catch. Now, this is an important point. I'm going to draw first the stub over here, and it's got a short for the load, and we're going to find this length, and I'll just call it L stub here. And remember, this is going to assume a characteristic of impedance of Z naught. Now, I've got to show you something here that you need to appreciate, or you'll mess these things up, left and right. Here's my mini Smith chart that has to do with this guy right here. This has to do with this, okay? Now listen to me. Remember, we're in the admittance domain, not impedance, correct? If we have this and it's a short, what is the impedance of a short circuit? 0. Do you all agree with that? Normalize 0. 0 divided by anything is still 0. Take 1 over that. What do you get? Infinity, right? The point, now we're working in the admittance domain, so we get the normalized admittance at the load for this thing. Here's the infinity point. Look at your Smith chart. Right here, this is the infinity point. And if you have a shunt stub tuner that's shorted, this is the starting point. Y'all with me? Can you look at it in your Smith chart? You see how that's infinite, right? The circles get smaller and smaller and smaller radiuses until they go to infinity. Can everybody see that? Far back? Over here, guys, you got it? So you're going to start right here. Now you'll notice one thing. When you move, this has a value that is always on this rim. It's always going to be on the outer rim. There is no real component. When you move, you're going to see minus J something large, right? Take a look. And as you move, you can see that all the values, as you start out and you move from there, they're all negative J, correct? This is admittance. You all with me, class? We want a value that minimizes this length. That's minus J, so we want 1 plus positive J on this side. So when we add it in parallel, it'll kill it off, but it will cause this length to be the shortest. Do you all hear me? How many understand the reasoning behind it? All right? No, come on. I mean, this is not that hard. If you want the minimal length here, you want the length of this line, which is going to have a minus J sense, right? So that means when you move, you would want this to have a plus J sense, right? If you moved here, this is a minus J sense, then you would have to go all the way from here on the rim to the positive J side, a full quarter wavelength away. You all follow me? Reason it through with yourself. Convince yourself. So make sure you do these problems. Because I promise you, when I say minimize the length of the through line or of the stub versus the length of the through line, people mess this up royally because they're really not sure. They kind of just guess, and they usually get it wrong in a big way. So I'm trying to warn you, I'm trying to politely encourage you to do these things as best I can. Can't force you to do it. Okay, now that's J 1.38. Y'all hear me? We're going to use that point. We figured out the length. Now we're going to put a stub in parallel. So at this point, we're going to have a transmission line with a short on it. It's called a stub. And we're going to figure out this length of the stub here. And then after that, basically, we've got something matched. So we're going to assume that this line right here is a characteristic impedance of Z naught, which is 100 ohms, which is fine. Right? Everybody with me? So now now we start moving. Remember, we normalized that short circuit's impedance. Well, 0 divided by anything is still 0, so we start at the right point. We're already normalized. Now we have to move, and we got to normalize admittance until we find, do this on your Smith chart. Tell me where you see the line coming in here as minus J 1.38. I think it's down a little further. It's probably about here. And it's going to be minus J 1.38. You'll see minus, like, actually here's 1 here, so it's right about here. And if you draw a line right from the center of your transmission, or of your Smith chart, right through that point, you're going to see something that says blank wavelengths towards generator. I need you to take a look at that. Can you all find that minus J 1.38? It's on the outer rim. It's the, and now it's a good mark, right? I mean, this is the imaginary trajectory, if you will. Can you see it? You got it? Over there? Take your time and find it for yourself. And man, a big Smith chart helps, and it helps it. If you need glasses to bring them, because I need glasses to see this. You guys, how many see this right here? Anybody else? Jeremiah, can you show me where that is?
Got it.
All right. Everybody? All right, now, look. Listen to me now. Now you take your straight edge and you got to draw a line from the center of the Smith chart right through that point, and you got to tell me what the wavelengths towards generator is that you read there. It's going to be 0.3 something.
0.35.
Point what?
35.
0.35?
0.355.
0.355. Do I hear a 0.35?
No.
0.355. Is that about right?
No,
It's
I
like
don't.
about like 0.351, 0.352.
All right,
Oh.
0.35.
Oh, yeah.
Look, I'm going to give you, I don't care about this. All right, listen, 0.35 something. Yes, sir.
I just wanted to ask, what is the acceptable answer for the sake of an exam question on something
Like
like
what's
this? Like, is this
plus or
3%, half a percent?
Oh, come on. I mean, if it's close, I'll give it to you. I mean, if you tell me it's over here, you're not going to give it, right?
So, like, for example, in the earlier problem, everyone got close to J plus 1.38, and I got like 1 plus, J 1.28. I'm around my compass.
I'm going to level.
This is what I forgot my compass.
You get sued for that.
Yes, exactly. So, barely, it's going to be right here with my road. Technically, this should not be, it should be a little bit.
How have you been drawing?
Yeah, it's like literally like see, obviously, the issue came from the free drone.
Oh, gosh, yeah, come on, man. I mean, don't ask dumb questions. Come on. He's got a circle drawn by freehand, and he expects, well, I'm off. No kidding. Me too. If you draw it with freehand, you get an F. I mean, bring your compass. All right, I don't give points for morons. I mean, basically, if I say bring your compass, it means bring your compass. That's all I'm telling you. All right, I'm just kidding around with you, but I'm telling you, that's the feeling. You didn't need that question. It's just
Well,
I drew a freehand.
to me personally, sir, you're right. My focus wasn't on the issue of the accuracy with or without compass. It was, let's say you
I give you, if you're doing the right thing, the points match up. If you can't read exactly right, I give you small, all right? It's going to be different, fat pencils, small pencils. Depends on how big your Smith chart is, all right? But I can tell in a heartbeat if you know what you're doing. I see where the points are. If they don't add up, and here's what I'll do. I'll see it's supposed to be here, and a person will have it here. And then they'll argue, well, I meant to put it there. Well, why didn't you? And then they come up with some bizarre answer. You've got to know what you're doing. If you know what you're doing, believe me, I will figure it out, and you will get full credit. But don't try to do stupid stuff where you get 4 or 5 different things and all these erasers and points all over the place and take a guess. And then you come and argue with me about, oh, I meant to do that. No, you didn't. All right, you all with me, class? Now, here's how you get the length of this thing. All right, hear me. You go from this point right here, which is 0.25 lambda, wavelengths towards generator. Take a look, make sure you see that. Y'all with me? And you're going to take this point you ended up at, that's how long this shunt stub is, and you're going to subtract that from it. So this distance, L stub, is really the point I ended up at, which is about 0.35 minus 0.25. So the actual length there is about a tenth of a wavelength, roughly. 0.1 lambda. Do y'all follow me, class? That gives you the length of that line. Now, that means if you take that and put it in parallel here, we're in the admittance domain, everything on this side of the Smith chart, or everything on this side of the transmission line, right here is impedance matched. The reflection coefficient right here will be 0 because the net impedance or admittance looking this way is identical to Z0 on that side. That's what we're up to. We're trying to make sure the actual impedance or admittance looking in to the network that you add to the load has really an impedance that's just Z0, and therefore there's no reflections. Y'all with me, class? How many understand the concept? We're going to do another. By the way, is the solution right for this one? Can anybody look that up?
Yeah.
Is it?
Yeah. 0.104.
Yeah. I'm not going to. Nobody gets killed if you're like 0.103 or 0.1. Yeah, right? I understand, right? I can look at the points and I can tell in a heartbeat if you know what you're doing. Do me one favor though, label the numbers. Y'all hear me? If you want full credit, I don't try to take a lot of points off or anything, unless you really don't know what to do. If you start here, you can label that point 1. It doesn't have to be point 1. But this point has to be labeled. If it was 0.2, this would be 0.3, and then over there, that would be 0.4. Yeah, your mind.
Where's that number 0.4?
This right here, this number. Is that what you're talking about?
The last B is
Yeah, that's just the length difference between here and here. Just listen to me. If you don't understand this, hear me now. I ended up at a point that has a mile marker of 0.35, approximately, lambda. Y'all see that? That means my length, here's where my stub started, where Y the stub normalized this, which is 0 ohms or infinite admittance. You start right here, you move till you move here. It's a very small amount. So you take this mile marker, which is 0.35 roughly, subtract 0.25, you get about 0.1. It's actually 0.10 something. Y'all agree with this, class? Did you follow me now, Jim?
So that 0.314, subtract that
0.35 is where we landed. Take that, subtract 0.25. Here, we're right here, this is 0.25. Can you see that? You understand why I'm there, class? Everybody understand why I started right there? Okay, we're going to do another. Did you ever?
Quick question. You said that shunt indicated parallel.
Parallel.
What wording, is there one that indicates?
Series is series.
Okay.
Shunt is parallel. That's it.
Okay.
He says he wants a series element. It means in series. If he wants a shunt element, it means in parallel. That's it. Everybody with me? Okay. I hope I answered. By the way, I'm just kidding around with stuff. Sometimes a little lighthearted humor helps when it's a rainy day. Are all you guys going to the game? How many are going to the game? I don't think it's going to be rain.
Don't say that.
I'm going to warn you about those games. I have got fried out there in the sun. I mean, like, burnt to a crisp sideways, so I warn you about it.
It says cloudy right now.
Good. I'm all for cloudy. I don't think I'm normal, but I might need that. All right, we're going to do another one. Anybody want to pick out one, or you want me to pick it out? This is a good problem.
usually just be flat.
You never, this happened. This happened.
I don't like it.
At least it's not At least I'll stand up. At least it's not gotta own this
Let's do problem 240.
Oh, yeah.
Can you hear me, class? It's problem 240. So for problem 240, it's another shunt stuff, but I prefer to do these, and I got a comment about this too. Where you have a load, you need to find this width of line, L, and we're going to connect something, but it's going to be in shunt or parallel. So we're going to have a transmission line that's connected in shunt. It's going to have a certain length, L stub here, and it's got a characteristic impedance of Z naught everywhere. We're going to do this problem, okay? Let me try to draw my Smith chart, yield Smith chart. And it looks like this.
I think the worst mistake I make is I forget to write J. I've never done that before.
Remember, in shunt, everything is admittance. All right, but we start by finding the normalized impedance. By the way, what is ZL for this one, class?
It's 25 plus J90,
Plus J90, and what is Z naught?
50 ohms.
All right, so when we get ZL, which is Z load over Z naught, that's going to be equal to 0.5 plus J 1.8, right? Isn't that right, class? All right, locate that on your Smith chart first. So that's 0.5. The 0.5 circle is somewhere about here. I'm drawing this this is about 0.5, and then J 1.8 is somewhere up here. J 1.8 is about here. So the point of intersection is somewhere up here. This is ZL. Can you all find that, class? What's my next step based on the last problem? You don't have to do sequentially in this order, but what's the next step? You can draw a straight line from there right through the origin, and while you're at it, you might as well just take your compass, start there and here, and then get a circle like this. So either one of these two steps, and then a straight line right through there. And what am I looking for on the other side? YL. I'm looking for this point right here, which is YL, which is 1 over ZL. And if somebody would be so kind as to do 1 over 0.5 plus J 1.8, tell me what that value is so you can confirm what you see over here. Anybody? Just take 1 over 0.5
It's
plus
0. It's 0.14 minus J 0.51.
Minus J, say it again.
5.51.
0.91?
5.51. Yeah.
0.51. All right, can you find this point, guys? What's next? Now I've got that point. I drew I know where YL is, right? What's the next step? U. How about we get the mile mark where YL is at, right? Take a look. I need to find out here what the wavelengths towards generator point is. It'll be 0.4 something, it looks like. This is drawn right. I'll take it. I'm not trying to run through this. Can you see it, sir? I mean, anytime I see people squinting, it's usually my writing. I'm trying to make sure you can read what I'm doing. Are you with me on this? What do you get for that, Ken? The mile marker down here. Now remember, take it straight through, look where the line comes through. 0.421, anybody else? 422?
Yeah, 0.422.
All right, we're going to go 0.422. 0.422 lambda, right? All right? This is our starting point where we're going to start moving. We're at the actual load impedance. How far are we going to move, class? we're going to move until we intersect the one circle. Unfortunately, the one circle is about superimposed on that. So we're going to move to this point, and it's 1 plus j blank, and you can tell me what that is. Now, this is going to be close to the point we started at. Not overlaying, but close, I think. Y'all see it, class? What do you get for this? I mean, let me do it this way. Take your compass or straight edge or whatever, and draw a line right through here. Draw a line right through here, and give me the mile marker wavelengths towards generator that we end up at first. Remember, this is a circle. It's got to be on the one circle plus j sign.
0.9195.
Say again?
0.195.
I would say 0.197, but yeah.
198, yeah.
195 is good enough for me. All right? If you're worried about resolution, that's good enough. Round to 3 decimals. All right? Now we're going to assess how far we have to move before we attach the shunt stub. You all hear me? All right. If you take a look at this, this is the mile marker I ended up at. This is the mile marker I began at. So total length here would be where I ended up, 0.195 minus where I came from, 422?
422, yeah.
All right, now that's negative, right? What do we do? 0.5. Tell me what that number is.
0.273.
0.273 lambda. That's just beyond a quarter wave. Just beyond a quarter wave. Y'all follow me? All right. Yes.
So what's that 1 over Z?
This is 1 over the impedance. Remember, we're in the admittance domain. This is ZL. This point, which is at the conjugate point of the circle, constant reflection coefficient, is just 1 over ZL. Can everybody confirm that? You all see this? You can get, it's easier to get this point just taking a straight line through the center and putting it there. I promise you it's much easier doing that than taking 1 over ZL, because these numbers are getting a little tough to read sometimes. I'm just letting it. Very tough. Okay, we're there. Now, what's next? There's going to be some markers thrown down here. What do we do next? We got the length. What do we need? I need this point. It's 1 plus j what? Anybody? I mean, what do you get? Say it again. What? Is that right? About that, class?
Wait.
2.6. J 2.6. All right. Now we know what we have to eliminate, right? Now he said to minimize the stub, and it's shorter. Remember, and I'll draw my little thing over here. Actually, let me draw it over here. So, again, we're starting with a stub that's got a short on it, right? Z of the stub is got, the load, I'll call it Z load is 0. That means you normalize it to infinity. So Y of the stub normalized is infinite. You all follow me on that, guys? Now we're going to start moving. So where are we over here on the old Smith chart? We're right here, aren't we? This is our starting. This is the infinity point, right? That's what we're going to start at to calculate the value of the stub we need. You all follow me? I really need your attention here. Do you have a question? If you do, just ask.
What's the variable in the ZL?
It's just the stub. It's 1 over ZL. Y stub, I'm looking at the load right here. It's a short circuit, so the impedance of a short circuit is 0 ohms. Normalize it at 0. That means the starting point right here for the stub impedance at the load, is just infinite. That's 1 over. Y'all with me? I'm just trying to indicate that. This is the starting point, right? Now we have to find a value when added in parallel. Right, such that it gets rid of the 2.6. Now, I need your eyes for this guy. Come down here, you're going to see, I want to say it's about here, and it's going to be minus J 2.6 here, and then you have to take your ruler, go from the center, drop right through there, and you're going to find something with Wavelengths towards generator. I need that value because we're going to find the distance. Y'all follow me? We started at 0.25 at the load. And yeah.
Why is it negative J 2.6?
Remember, we have a plus J 2.6 here.
Oh, okay.
We've got to get rid of this by adding a minus J 2.6. And there are no dumb questions here. It's freehand.
That was the point.
I'm just playing. I had one guy that it's a class in electrical and computer engineering. He'll ask something about soil rotting or the score of a baseball. Those I can call dumb. But any other question related to the classwork is not dumb. All right, can you find that there's a trajectory that's going to come in perpendicular like so? Can you see that?
Yeah.
All right, and see where it says 2.6. You should be able to see. I mean, I don't have my Smith chart. Can you show him? If you look on the edge there, they're numbered, right? Aren't they?
Yeah, okay. I was like,
All right, if you did the math on this, let's say 0.175 minus 0.422, that's negative, right? Can you have a negative weight? No. So every time you go around the circle, the full, or all the way around, 360, halfway, right? So you add that 0.05 to account. That's it. Y'all with me?
Oh, okay. Yeah.
All right, now, bear with me. What's this value? Guys, anybody?
0.30.
Say it again?
0.308.
Is that it? 0.308, right? Hear me? So how far do we move? What's wavelengths towards generator here? 0.25 wavelengths towards generator. I ended here. I started here. How far is it?
0.052.
All right, so the length of the stub is going to be 0.308. I got a comment here. I need your attention too when I say this. Minus 0.25. And what does that say again?
0.052 lambda.
All right, listen, this is important. For a for a transmission line, to look like a transmission line, where wave phenomena will be developed, the cardinal rule is that it has to be a tenth of a wavelength. You hear me? If you got just two short pieces of metal that are like hundredths of a wavelength, they're short circuits. They don't look like a transmission line. We're down here. We have got only 0.052 lambda, right? Not even a tenth of lambda. Technically speaking, this would fail. You would add, in order to do it right, you would have to add a half wavelength. Now, Wentworth's book doesn't have, you all with me on this? Every time you add a half wavelength, the impedance is the same. If you add a half wavelength to that, then it's 0.552 lambda. You all see that? That would be something that would have an impedance that's exactly what you want, or an admittance that would match it. But when you're at 0.052, in his book, that's going to be his answer, I think, if you check. You're actually dabbling in the things that won't work. Anytime you get less than a tenth of a wavelength, add a half wavelength to that distance. In the real world, and I'm telling you this, I haven't had any problems in the real world doing this, but you may come across it. Just remember that. Because things don't look like transmission lines if they're less than a tenth of a wavelength long. There's a certain length so wave phenomena can be developed. All right? Just saying that. Do you understand this? I know I'm over. Okay, guys. Thank you for coming. I'm going to ask you to do that homework now. On Wednesday, we get a quiz. The quiz is on distance. And I'm going to start I'm going to ask you to do all the problems in that section. I'm going to give you a few others. I'm just warning you guys. Huh?